Good, so welcome to this chemistry masterclass from Cambridge Leadership College. We're working on the A2 level chemistry paper in this masterclass, looking at a structured paper from the summer series in 2016. It's a 2-hour paper, a bit of a monster, so it's going to be tough to get through a 2-hour paper in a 1.5-hour masterclass. So what we'll have to do is we'll have to skim over some of the things that I think are fairly straightforward or easy to look up. But when we look at the examiner's report, the examiner, chief examiner, identifies some questions as particularly discriminating. And what he or she means by that, of course, is that these particular questions really show the difference between the A and the A-star students and other students. These are discriminating questions. And as you read the examiner's report, the examiner starts off by describing some of the questions as discriminating. And then as you go through the paper, the examiner starts to say that some of the questions are very discriminating. And by the time you get to the end of the paper, the examiner has kind of given up and said, some students didn't even answer this question. So that's as discriminating as it gets. So we'll try and tackle these questions that students found hardest, the examiner says is discriminating, as we go through the paper during this masterclass. All right, well, we can start off then. And actually, the examiner said that the starting point of this exam was a very kind of generous and gentle introduction. These questions about group 2 metals, the reaction with carbon dioxide, and the group 2 hydroxides, it's all relatively straightforward and things that can be quite easily looked up in revision notes or textbooks. So this was quite well done by the students, and I'm not going to spend too much time on this. If we've got time at the end, we can come back to it. But really, you need to know that the solubility of these hydroxides increases as you go down group 2. And that's the kind of key that unlocks a lot of this work on this question. And then you come down here, this question about the thermal stabilities of carbonates in group 2. Well, if you've done a number of these A-level questions, it's almost as if a question about the thermal stability of carbonates as you go down group 2 is in almost every single paper. So, that's a really very, very important part to learn. And you just need to know, of course, that as the cation becomes larger, then the charge density becomes less. And so the cation can no longer easily polarize the carbonate anion. And that's the reason that the thermal stability becomes more stable as you go down the group. So I'm not going to do these questions that much. If we have time at the end, we can come back and look at them. But I do want to just look at question 2. And what I want you to notice actually is there's here, there's a whopping 5 marks for a question. And I don't think anywhere else in the paper they're awarding 5 marks. And all you've got to do is know a couple of colors of cobalt complexes. So you can see these are things that you can't work out for yourself. They're just some things that you have to learn. And a lot of students, I know from speaking to them, go, oh no, I've got to learn the colors of these transition metal complexes. But actually you can see that with a bit of investment in learning the colors, then there's a really rich or a mark-rich question here that's going to give you 5 marks if you can answer that question properly. And all you've got to do is know that the cobalt complex in water has 6 water ligands. Excuse my writing there. And has an overall charge, just getting this pen working this evening. It's not that easy. So that's the aqua complex. And when you add concentrated hydrochloric acid, then the water ligands are replaced by chloride ligands, and you have 4 of those. And then the overall charge becomes 2-. And you had to know that the aqua complex was pink, and the chloride complex over here was blue. Now you can only fit 4 chloride ions around because these chloride ions are much more sort of bulky than the water ligands, and that's why you can fit 6 water ligands around, but you can only fit 4 chloride ligands around the central cobalt cation in the center there. And so, of course, with 6 water ligands, then the shape of that is octahedral. And with 4 chloride ligands, the shape of that is tetrahedral. Now, compared to how hard you have to work later on in the paper to get marks, I think that's a pretty easy set of 5 marks given away right at the start of the exam if you know these colors. And there's no kind of shortcut to that. That's just something you're going to have to study and learn. But you can see your study is well repaid at that point by having this very mark-rich question. And it seems to me you're not having to work very hard to get the 5 marks. Okay, so then coming down to looking at complexes of nickel, and you've got to end up with these kind of diagrams where you've got a central nickel cation in the center, and then because you've these 2 nickel complexes here have 2 isomers, that's the clue, isn't it? That you've got to be able to draw these isomers. So those, my very bad drawing. These are the bonds coming out of the plane of the paper towards us, and these are the bonds going behind the plane of the paper. And you've got the iodine ligands there, and you've got these other ligands here. And you can see that that is a cis isomer, and it's easy to draw, isn't it? The trans isomer. You've got an iodine there and an iodine there. So you've got your 2 geometric isomers like that. And really, you should, I don't think you did it in the mark scheme, but if you did RP, if you did that, I think the mark scheme gave it to you, but because the lone pair of electrons that's forming this coordinate bond here is being donated by the phosphorus atom, there could be other exams where they don't accept that you've drawn that ligand that way around. So you might need to check the mark scheme, but I think they probably didn't pick you up on that on this time, but you should draw the phosphorus there and the 3 alkyl groups there, because it's the phosphorus that's donating the lone pair of electrons to form the coordinate bond. So make sure that you know, it's a really easy mistake to make. I don't think they penalized it on this occasion, but when you're drawing, well, these kinds of complexes, and actually other displayed formulae as well, you've got to make sure that you show the bonds going to the right atom. And then this one down here has only a single isomer. This is the cobalt complex, and with the cobalt complex, then you've got this tetrahedral shape, haven't you? Like this. And again, you'd have to check the mark scheme, but you should have the phosphorus there and the 3 alkyl groups there, and then you have the 3 alkyl groups and the phosphorus like that. That's the correct way to draw it. I don't think they penalized that in the mark scheme. But you can see here that this central cobalt atom doesn't have 4 different groups attached to it. It's got 2 iodine ligands and 2 of these phosphorus ligands here. And so only if those were 4 different ligands would that have optical isomers. And because it doesn't have 4 different ligands attached, it doesn't have optical isomers. And so the lead into the question says, well, there's only 1 isomer of that, but there's 2 isomers of the nickel complex. So these are cis-trans geometrical isomers, and there aren't optical isomers here. There's just 1 kind of isomer. Good. All right. Okay. The point that the examiner made here was that, and this is we've seen actually in several mark schemes, is the question is asking for the equilibrium constant in terms of partial pressures, and a lot of students are giving the equilibrium constant in terms of concentrations. So don't do that, because that ends up with square brackets denoting concentrations. That's wrong. You've got to have the equilibrium constant in terms of partial pressures, in which case you're going to be drawing that the equilibrium constant is, that's a P for partial pressure, isn't it? And then you put the chemical formula as a subscript, and then you've got the pressure of hydrogen, the partial pressure of hydrogen, that's as a subscript. And then because you've got a stoichiometric coefficient of 4 for the hydrogen over here, you're going to have an indice of 4 up there. So you can see that I'm correctly giving the equilibrium constant in terms of the partial pressures. I haven't drawn square brackets, which would have indicated the equilibrium constant in terms of concentrations. So just completing that, that's the partial pressure of hydrogen sulfide as a subscript times the partial pressure of methane as a subscript, and I put that in brackets because there's a stoichiometric coefficient there too, which is going to become the indice there. All right, so that's the examiner just keeps flagging that up, that lots of students are ending up writing concentrations, which would be correct for an equilibrium constant in terms of concentrations, but you've got to write partial pressures for the equilibrium constant in terms of partial pressures. Then this question here was one of the ones that the examiner said were discriminating. And really, these questions on determining various calculations at equilibria are all made, I think, very, very easy if you lay out an equilibrium table. So I'll just talk through that now. So you've got this reaction. I'm just going to write it out again. So that's the hydrogen sulfide, that's the methane. We've got a reversible reaction. We've got carbon disulfide, and you've got hydrogen there. And these equilibrium tables, you lay out them with I, which stands for initial, C, which stands for the change, and E for equilibrium. So your mnemonic here is ice. Now it tells you, doesn't it, that the initial partial pressures, so that's my I for initial partial pressures were 200 and 100. And then it tells you here the equilibrium partial pressure, so I'm coming down to this E part here, was 2 atmospheres for that and 98 for that. Okay, so what's happening here is, if you had this, that was the initial there, wasn't it? That was the equilibrium. So the change, we might say, well, you've got, if there was a change there of x, you'd have a change there of 4x, and this would be 100 minus x, and what would this be over here? It would be 200, but the stoichiometric ratio between that one there and that one there is 1 to 2, so that's 200 minus 2x. Can you see, once you set up these equilibrium tables, things start to fall into place. Now, So that was the that change line there in my equilibrium table. And they gave us some of these values at equilibrium. Well, if x equals 2, 4x must be 8. Easy stuff. And 100 minus x, they gave us that for 98. And 200 minus 2x, well, that's going to give us 196. So that's the hard work done, really. And if you sort of follow this way of laying out your work with these equilibrium tables, the initial, the change, and the equilibrium values, then things work out pretty easily for you. And once you've got that, all you're doing then is plugging the numbers that you've calculated here, yes, into the expression for the equilibrium constant in terms of partial pressures that you had right at the start of the question. And so you're going to work out a value of Kp, which is going to be equal to 2 times 8 to the power 4. These are these numbers here, aren't they? And then the denominator is 196 squared times 98. Okay? So you've got all those values from your equilibrium table, and you've got your expression for the equilibrium constant up here. You're just plugging the numbers in at that point, and you end up with a value down here of 2.176 times 10 to the minus 3. Now, strangely enough, you're only getting 3 marks for this. Can you see what I mean about the 5-mark question earlier? You were getting a lot of marks for not working very hard, as long as you revise your colors of transition metal ions. Normally, these kinds of questions, where you have an equilibrium table like that, sometimes they give you 5, sometimes they give you 6 marks. So again, these equilibrium table type of questions are typically mark-rich questions. And if you can do them, and I don't think they're very difficult, if you lay them out like this, you're on your way to gaining a nice number of marks for something that I think, once you've got the technique, works out fairly straightforward. Okay, good. Okay, so this one here, well, all the examiner is getting you to think about here is, you probably read in your textbooks that entropy is a measure of disorder, how disordered a system is. And all the examiner is getting you to look at here is that on the left-hand side of the equation, you've got 3 molecules of gas, and on the right-hand side of the equation, you've got 5 molecules of gas. So you'd have to say on the right-hand side of the equation, that is a more disordered system, because you've got 5 molecules of gas rather than 3 molecules of gas. It's more disordered. And if it's more disordered, then the entropy is going to be greater on the right-hand side, and so that the entropy change is going to be positive for this reaction. Okay, so we're expecting it to be positive. We've now actually got to go and calculate it, and you've just got to recall at that point that the Gibbs free energy is equal to the enthalpy change minus the product of the temperature in Kelvin times the entropy change. And that's what you're trying to work out, isn't it? So all you've got to do is remember that equation, and then you've got to rearrange it so that the entropy change, delta S, is the subject of that equation. And if you rearrange that, then to have the entropy change as the subject of the equation gives you delta H minus delta G divided by the temperature. Now they give us, don't they, delta H, it's over there. They give us the Gibbs free energy change, it's there. And they give us the temperature, it's there. So you've got delta H, you've got delta G, you've got the temperature in Kelvin, you plug all those in, and you're going to end up with a value for the entropy change. If you just watch your units there, this is in kilojoules per mole, that's in kilojoules per mole. That's so the values of the enthalpy change and the Gibbs free energy change are consistent. One of the things that you have to watch in some of these questions is that you sometimes have a value there that's in joules and a value up there that's in kilojoules, and so you have to change one of them to joules or the other one to kilojoules. But on this occasion, they're both in kilojoules. You can just keep them as they are, and you end up with an entropy change of 0.19, and the units up there are kilojoules per mole divided by temperature, so it's kilojoules per mole per Kelvin. Kilojoules per mole per Kelvin. You can just work that out by substituting the units into the rearranged equation that you've got there. And those are your units in there. All right, so in this part down here, it's just getting you to think about, well, how does this value of delta G change as this value changes? Now, the enthalpy value we've got is, what was that? The enthalpy value was plus 241. And this term here, eventually, as you increase the temperature, this term, T delta S, is going to get bigger and bigger and bigger and bigger as the temperature gets larger and larger and larger. So this term will become increasingly negative until you get to a point where it's so negative that when you subtract it from delta H, the answer, delta G, is itself negative. And when you get to a value of delta G, the Gibbs free energy, that is negative, that's the criteria for whether a reaction is feasible. Delta G has to be negative. And so what's going to happen here, as you increase the temperature, eventually this whole term becomes sufficiently negative so that when you subtract it from delta H, delta G is negative, and if delta G is negative, then the reaction has become feasible. So your answer here is saying that the reaction is becoming more feasible as the temperature increases. All right. I think this one, it wasn't really a discriminator. It was more a mistake that lots of students made. So because you're used to, aren't you, writing definitions for a standard electrode potential. And so you see something that looks like an electrode potential here, and you see the word standard, you see potential, and all the students start writing a definition for a standard electrode potential. But you've got to write here the definition for a standard cell potential. And so the examiner picked up that loads of students are kind of not reading the paper carefully enough and are just jumping in and writing a standard electrode potential. You've got to write a standard cell potential. And with the cell potential, you've got your two half cells, which have standard electrode potentials. And if you've got your electrodes in each half cell, you're measuring a voltage here, and you're measuring a difference, aren't you, between the potential here and the potential there. So somewhere in this definition, I think the examiner is expecting to see you're talking about the potential difference under standard conditions when you measure the potential difference between these two half cells here. So I know in the mark scheme it talks about electromotive force. I don't really find that's very, very helpful. It's much more helpful to think about the potential difference, because you've got a voltmeter measuring the difference between here and here. So to think about it as a potential difference, it's a more useful way of thinking about it than saying something like the electromotive force, which I think got you the mark in the mark scheme. But if you think about the standard cell potential as a potential difference, then that's helped your thinking about these kinds of systems. So I'll be putting down potential difference there rather than electromotive force. Okay, big health warning on this question. is in the mark. Well, okay, let's just, I'll tell you what I think in a moment. Okay, so if you look up in the data book, everything in the data book is written as a reduction, isn't it? So you've got that going to Fe2+. And the standard electrode potential for that was plus 0.77 volts. And then you've got this other standard electrode potential for silver, written as a reduction, and that's going to silver metal. And your standard electrode potential for that is 0.8 volts. Now, which of these is the most negative? I know they're both positive, but you have to think in relative terms because we're thinking about here potential difference. It's all about the difference between things rather than their absolute values. And so if I look at those two, I mean, they're very close together, but I would say that one is the more negative and that one is the more positive. Yeah, you can see that's 0.8 and that's more positive than 0.77. So I'm saying that one's the most positive and that one's the most negative. And in some A-level syllabuses, you have to learn what's called cell convention. And cell convention always has the most negative on the left and the most positive on the right. So I think on the right, you've got in here, you've got this solution of Fe3+ and Fe2+. And over here, because this is the most positive, you've got your solution of silver ions. Now, in the mark scheme, it swaps it the other way around. And then at the end of the mark scheme, it says, oh, by the way, it doesn't matter if you drew it this way around. So the mark scheme and your syllabus doesn't matter which way round you draw these things. But when you look at some examples in textbooks, some things are always easier if you follow cell convention and have the most negative on the left and the most positive on the right. So even though the mark scheme and your exam board doesn't ask you to do this, it's a good habit to have the most negative on the left and the most positive on the right. Now, so if this is a silver solution here, that must be a silver electrode there. And for this, the redox or the half reaction is happening in solution, isn't it, between Fe3+, which is dissolved, and Fe2+, which is dissolved. And in that case, the electrode that you put in there is an inert, unreactive electrode made from platinum. And so I think it would be better to say that A is platinum, B is the Fe3+, Fe2+ solution, C is silver, and D is the silver solution. Now I know they swap those around in the mark scheme and that's absolutely fine, you get your marks, but it's a good habit to have the most negative electrode on the left, as I've drawn it up here. Okay, we're not quite done yet, are we? Because we've got to complete the diagram. We're trying to measure the potential difference. And the way to measure the potential difference between here and here is to put a high resistance voltmeter in there. And that'll tell us the potential difference between the standard electrode on the left-hand side and the standard electrode potential on the right-hand side. We're almost done. The last thing we need is a salt bridge. It's going to go in there to complete the circuit. And the only thing I'm going to say here, it's not asked for in this question, but sometimes they say, well, what would you have in the salt bridge? And some people say, oh, I know, what I'll do is I'll put in there a salt like potassium chloride, because you sometimes see that to go in the salt bridge. The problem with that, of course, is that if you've got a chloride ion, it's going to precipitate silver chloride with the silver ion there. So if you put in your salt bridge sodium chloride or potassium chloride, on this occasion it would be a bad choice because you'd start to precipitate out some of the silver ions as silver chloride. So, so potassium chloride is a bad choice. A safe choice, and you can never go wrong with this, is potassium nitrate, because all nitrates are soluble. So if some of the nitrate comes into here, it doesn't matter. Silver nitrate is soluble. So having a salt bridge with potassium nitrate is a safe bet because you're not going to get any precipitation with any other ions that are in solution anywhere else in the system. That's not asked for on this occasion, but it's just like a useful tip for when you're working with these kinds of problems. Okay, so typically at this point, you've got your two equations here. Now, this one is the most negative, isn't it? And the most negative one is going to be losing electrons because the electrons want to go to the most positive one. So the electrons are moving this way, aren't they? They're moving from the negative to the positive. So that means that this one is gaining electrons and reduction is gain. So that's written correctly. And if that's reduction is happening, this one is going to be reversed because it's losing electrons. Oxidation is loss. So you would reverse that and write Fe2 plus is going to Fe3 plus an electron. Oxidation is loss, we've lost an electron. And because we've reversed that reduction, then you reverse the sign of the standard electrode potential. So that's now 0.77. And then you add those two together, and you add those two, and you get a cell potential of 0.03. And your overall reaction is adding that and cancelling out the electrons. So you've got Fe2 plus, haven't you, plus silver ions is going to the silver metal and Fe3 plus ions. And the electrons have been cancelled out. And so what you want, because they asked for it down here, it says, write the equation. So we should be writing down that equation. And again, because some students are on autopilot, because they've done this so many times, the students are coming down here and writing the cell potential. Okay, because you're under exam conditions, you think you've answered the question you want rather than the question you're being asked. So it's just a danger that it's so easy to answer the question you want to be asked rather than answer the question that you are actually being asked. And lots of students were writing down here the cell potential, and they weren't writing down there what they were asked for, which was the overall cell equation. This one here, you've just got to plug some values into this Nernst equation. And when you do that, you find out that the value of the electrode, when it's not under standard conditions, but under other conditions, that the electrode potential is 0.77 volts for the silver electrode. And so if the silver electrode has 0.77 volts, because we've changed it away from standard conditions, and this electrode here has a standard electrode potential of 0.77 volts, then what is the potential difference? What's the difference between those two? The difference is nothing. The difference is zero. And so you've got to do a calculation there, work out that the electrode potential for the silver electrode is now 0.77 volts. And when both electrodes are 0.77 volts, then the potential difference is zero. The value that goes in there is the voltage of the cell is now zero as well. All right, good. What did the examiner say here? Okay, so you're looking at this carboxylic acid, and it has a carboxylic acid group at each end of the molecule, and then some a carbon chain of varying length in between the two carboxylic acid groups. And it's saying, well, actually, this first dissociation is a much stronger acid than just ethanoic acid. And you've got to say why that is. Well, when you've removed one hydrogen ion, you've got a negative charge here. And if you've got a short carbon chain, then this carboxylic acid group can draw the negative charge towards it. And that negative charge then gets distributed over the whole molecule, and the distributed charge leads to a more stable anion. And that's the reason that this is more acidic, is because the anion, compared to the ethanoate anion here, the anion is more stable because the negative charge has been distributed over the whole molecule because of the electron withdrawing capability of the carboxylic acid group here. And then there's a question here that removing that proton is relatively easy because the anion is stabilized because the negative charge is spread out over the whole ion. But this second step is much harder. It's much harder to take a second proton off. It's much harder to take that one off than it was to take the first one. And the question is, why is that? Well, look what you're doing. You're trying to remove a hydrogen ion, H+, from something that's already negatively charged. And so that is not electrostatically favored because there's an electrostatic force of attraction between the hydrogen ion you want to remove, which is positively charged, and the negatively charged anion that you've got there from this first step. And so trying to remove something positive from something that's negative is not electrostatically favored because there's an electrostatic force of attraction between the positively charged hydrogen ion and the negatively charged anion. Let me see, just trying to find the things that the examiner found that students were particularly finding particularly difficult. Okay, I'm going to move ahead because this next, we can come back to it if we have time at the end, but I'm going to move ahead to this next one here because this is one of the ones where students found, or the examiner found, that this was quite discriminating. All right, so look at this first part here. We've got this nitrobenzene, and it's being reduced to this amine over here. And we've got to balance this half equation. All right. Now, I'm going to go through a couple of ways of thinking about that because they are there's different ways you can think about this. One of them, there's an absolute bomb-proof, absolutely sure way of getting this right. If you're working in acid solution. So the method I'm going to show you only works in acid solution. Don't try and make it work in alkaline solution. It doesn't work. All right. So you've got to balance this equation here. And the first step, when you're balancing an acid solution, is to balance oxygen with water. So balance oxygen with water. Okay, that's your first step. Excuse my bad writing there. So you've got two oxygens over here. You're balancing oxygen with water. If you've got two oxygens, you must have two water molecules. Now we've balanced oxygen with water. Great. Second step is to balance hydrogen with hydrogen plus. Okay, so let's have a look at that then. So we've now got on this side 2 times 2, so that's 4. And we've got another 2 there, that's 6. So we've got to balance hydrogen with H+. So we've got 6 hydrogens over here, we must have 6 over there. Okay? Third step, balance charges. Now on the right-hand side it's no charges, overall neutral. And on the left-hand side here, we've got 6 hydrogen ions, so therefore to balance charges, we must have 6 electrons. And so we're done. That's the technique for balancing these half equations under acid conditions. Balance the oxygens with water, balance the hydrogens with hydrogen ions, balance charges, and you're done. Another way to think about this is to use oxidation numbers. And the difficult thing is that as students, you don't know, well, it's difficult to figure out, isn't it, what the oxidation numbers are in this organic compound. And you know that this is a reduction, the nitrogen is being reduced. So if we wanted to follow that reduction, we want to look at the oxidation number of nitrogen. Now these oxidation numbers, they're a kind of almost chemical trick. They're just a way of trying to figure things out. And oxidation numbers mean that you have to imagine in your head that even though this is an organic compound with covalent bonds, you're going to imagine that it's ionic. And that's the way these oxidation numbers work. All right? So this is why oxidation numbers are kind of trick. They're kind of technique for figuring things out. Now, I know this is organic, but if you had oxygen, normally oxygen is O2 minus as an ion, isn't it? And you've got 2 of those. And you've got something that looks like benzene over here, C6H5. Benzene is C6H6, and this is C6H5. So that's a bit like removing a hydrogen ion from benzene. And so if you thought about that as being ionic, it would be C6H5 minus. Yes? Now, to get an overall neutral here, you've got 2 lots of 2 minus and 1 lot of 1 minus. That's 5 minuses altogether. And so, in our kind of playing around with ions, that gives us a nitrogen 5 plus ion. Now, you can see this is all chemical nonsense. There's no such thing as an N5 plus ion. And there's no such thing as a C6H5 minus ion. But oxidation numbers are just a technique. No. They're just a technique where you think of things as being ionic when in fact they're not. This is just a covalent compound. But because you've worked out there from thinking about things as ionic that nitrogen has a +5 ion, you can call that a +5 oxidation state. And that's how you've worked out the oxidation number of nitrogen in that organic compound. Same thing happens over here. You've got C6H5NH2. Health warning, big warning, this is not ionic. This is a covalent compound, but to work out the oxidation number, you can think of it as being ionic. So you've got 2 hydrogens there. They're normally H+ ions, aren't they? And you've got this thing that we looked at before. We can think of that as being C6H5 minus. Add those all together, the nitrogen now must be N minus, because this is overall neutral. You've got 2 negatives, 2 positives. Think of that as N minus. Of course, N minus doesn't exist, but we're just using this way of thinking to help us work out the oxidation number. So the oxidation number of nitrogen is -1. So I'm now going to remove all of this because oxidation numbers are just a kind of trick or a technique for working out whether something's being oxidized or reduced. But you can see there that the oxidation number has gone from +5 down to -1. So if the oxidation number is going down, that is a way of identifying a reduction. And that is confirmed here, isn't it? So the other thing that you can do is finally, you can do a check here that if the oxidation number is going down, that's a reduction. Reduction is gain from your mnemonic of oil rig. And it's true that electrons are being gained, and you've got a change in oxidation number from +5 to -1. So the oxidation number has changed by 6. It's gone down by 6. So you would expect, wouldn't you, to be adding 6 electrons. And so you can do a check here, just to check where you could balance it here with water, with hydrogen by balance the charges. But sometimes you might also want to work with oxidation numbers and check that you're going down by 6 electrons because the oxidation number itself has gone down by 6 negative. Okay, all right, so you've got 1/2 equation there, and you've got implicit in here is another half equation because you're going from tin, which has a oxidation number of 0, and you're going down to an oxidation number there of oxidation number of +4. So if you wrote out the half equation for this, then that would have a loss of 4 electrons, and this one's got a gain of 6 electrons. And to combine those two half equations, you're going to have to multiply that one by 4 and that one by 6, and then you're going to have to cross out 24 electrons from there and 24 electrons from there. And if you work through all those steps of multiplying this one up by 4 and that half equation by 6 and cancelling out the number of electrons, then you can work out a balanced full equation from the two half equations that you had here. And so once you've done that, you end up with these stoichiometric coefficients for that combined redox equation from the two half equations. And that was one of the questions that the examiner said that students found difficult. All right? But it's, you know, you're starting to get worried, aren't you, when you start multiplying up by 4, multiplying up by 6, because you're not used to using such large stoichiometric coefficients, and you end up here with 24 electrons, and it feels like it's going wrong, but you've got to hold your nerve and know that later on you're going to be cancelling these large numbers of electrons to give you this combined redox equation from the two half equations that you multiplied up by 4 and 6 to cancel out the number of electrons. Okay, so now that you've got the stoichiometry there, you can work out percentage yields. That's fairly straightforward. And then down here, you're adding excess sodium hydroxide because you want to liberate this base here, because up here you had the ammonium, ammonium chloride salt. So to convert that from NH3 plus Cl minus to give yourself the amine down here, you've got to add excess sodium hydroxide, and that will liberate the amine. And you had to work out there in the mark scheme, they gave you a value of 3.016 grams when you worked that out. I was a bit surprised about that because you can see in the question that the largest number of significant figures you get there is 3 significant figures. And they give the answer here to 4 significant figures. So I'm not quite sure why they did that. It's much more natural, I think, to have written there 3.02 brackets, 3 significant figures. I mean, that's just not quite sure why they're expecting you to have 4 significant figures there when there are only 3 significant figures in the question. But strange, I'm not quite sure why that is. Okay, so you've got now this free base in a solution, an aqueous solution of sodium hydroxide. And they're now going to add in this solvent here, dichloromethane. And so what's going to happen is that base is going to mostly dissolve in the organic solvent, but some of it is going to be left behind, still dissolved in the aqueous solution, sodium hydroxide. And so this means that some of it is in the aqueous layer and some of it is in the organic layer. And because you haven't got, or you've got some of the amine still in the aqueous layer and some in the organic layer, you've got it partitioned between the two layers, between the aqueous layer and the organic layer. And you can describe that the solid is, some of it is in the aqueous layer and some of it is in the organic layer using this partition coefficient. So that's really just a special form of your equilibrium constant, because you've got your phenylamine, some of it is in your aqueous layer with the sodium hydroxide, and some of it is still the same compound, is in your organic layer. And there's an equilibrium constant for that. So, and that equilibrium constant is just called the partition coefficient. It's just an equilibrium constant. And so to work it out, you'd say, well, that equilibrium constant is the concentration of phenylamine in the organic layer divided by the concentration of phenylamine in the aqueous layer. So you just have to excuse my difficult writing here. I'm trying to speak clearly, even though I can't write very, very clearly. So, so this partition coefficient is just a special case of an equilibrium constant, and you've got your concentration in the organic layer, your concentration in the aqueous layer. You just divide those two, and you get this equilibrium constant here that they've called a partition coefficient. And you get a value, well, the mark scheme gives you a value of 3.99. If you carried forward the value from up there, which I think you should have done, because you had three significant figures rather than two significant figures, when you carried that forward, you ended up with a partition coefficient of 3.94. Normally with the mark schemes, they allow something called ECF, error carried forward. So if you had a value up here that you'd correctly rounded to three significant figures, and you got down here to have 3.94, then it's an error carried forward as far as the mark scheme is concerned, and you wouldn't be penalized for that. Okay, the examiner said that was fairly well known, that the lone pair of electrons on phenylamine is delocalized into the ring system of the benzene ring. So the lone pair of electrons on the amine is less able to form a bond with a proton from an acid. It can't act as a base as easily as ethylamine. So you had to explain that. Now this one, the examiner needed you to pay attention to. So you've got something here where you're making it's called an it's called a diazonium compound. And what it is that you've got an amine there on the phenylamine, and when you react it with nitrous acid, then you end up with this. You've got a positive charge there, and it's a salt. Okay, so and to do that, you need nitrous acid. And the problem with nitrous acid, you just can't go and pick up a bottle of it because it itself is unstable. So you have to make nitrous acid at the same time you use it. So that's called making something in situ. Now the way to make nitrous acid is to start with sodium nitrite and hydrochloric acid. And that'll give you the nitrous acid that you want to make this compound up here. And so the mark scheme said, well, you can either use that or that, it doesn't really matter. It's better to say that, because I know that's the reagent you want, but you can't go and get that. You've got to go and make it. It's unstable. So for step one, you need sodium nitrite and hydrochloric acid to make your nitrous acid. So those are the reagents, and the conditions, well, this nitrous acid is unstable. So you've got to keep things cool, otherwise, even though you tried to make it, it would immediately break down. So that's the reason, or one of the reasons, your conditions here are to keep things cool. Now that's a bit of a standout condition, because in a lot of organic chemistry, your condition is you need to heat something up for distillation or reflux. But here, you're keeping it cool. Typically, you have a kind of ice bath with some ice and some water in it to keep things cool. And not only is the nitrous acid unstable, but the salt that you're making up here can also be unstable as well. And so for those two reasons, your temperature, you're not heating it up under reflux or distillation or anything like that, is less than 10 degrees Celsius. So your condition is you're keeping things cool because you don't want to destroy the nitric acid that you've worked so hard to make, and you don't want to destroy this because you might want to use that in another step in the reaction. So that's the reagents. I think that's a better reagent. I know the mark scheme said that, but I think that's a better reagent. That's the reagent and that's the condition. And for step two, then this step is reacting with acid and water. So you've got to have boiling, and this time, because you're heating it and you don't want to lose anything, you're doing that under reflux with water. And you should also have dilute acid as well at that point, because what's going to happen here is you're going to take that, and because they haven't drawn this very well here, because that is the salt that you make as your intermediate there, and then in step two you're boiling with dilute acid. So that's acid dissolved in water, isn't it? And what happens is that breaks down to give you the nitrogen gas, and because you had the chloride there that was forming part of that salt, you're also going to be making HCl at that point, because you had the hydrogen ions here in your weak acid that you were using there for boiling and reflux. So you should be having your heating, boiling, you're under reflux, and you've got a dilute acid. You've got water and hydrogen ions, because you're going to convert this salt into this phenol here. You're going to release nitrogen, and you're going to make a bit of hydrochloric acid as well, because you had the chloride salt there. All right, that was all about amines, wasn't it? Now it's moving on from amines to amino acids. And in your data book, you've got, I didn't count them, but you know, there are, well, I suppose this is a question about biochemistry, isn't it? There's 20 amino acids that are used by the body. I didn't see in the data book whether 20 or not, but you can look up each of these amino acids in the data book. And the thing about the amino acids is any amino acid has an amine group. It has a carbon in the middle, and it has a carboxylic acid group there. And then it has something there, which is called the side chain for the amino acid. And all these amino acids are all identical. They have the amine group there, a central carbon atom, a carboxylic acid group there, hydrogen there. The only difference between them is they all differ in what's on that side chain. And so the simplest possible amino acid you can have is just to have that, which is alanine, I think. But they all vary from each other by the side chain that goes on here. And you can look up the different side chains in the data book. Now, to join amino acids together, you're forming a peptide bond. So that carboxylic acid of one amino acid is going to have a reaction with the amino group of another amino acid. So you're going to get a reaction between those two groups there. And because we're forming a tripeptide, there's going to be 3 of these carboxylic acid. It's going to be 3 of these amino acid groups. There's going to be 3 of these amino acids joined together. So because my writing is not good with these pens, I'm not going to attempt to try and draw these. You can look that up in the mark scheme. But the mark scheme is just getting you to look up in the data book the 3 different side chains that you get, a different side chain for each amino acid, and then you're going to be joining each of these amino acids to the other one with an amide bond. It's a polyamide. And then you've just got a bit of maths to do. You can work out the relative molecular mass once you've joined all those together. And where it's going here, it's saying, well, you can take those 3 amino acids, you can join them together, you can form a little peptide there, tripeptide. And if you did that experiment, you'd end up with a bit of a mess at the end, because once you tried to react them together, you'd have some of the tripeptide that's been formed, but you might get individual amino acids still around as well. And so if you separate them out using gel electrophoresis, then they're going to ask you here how the tripeptide and the individual amino acids are going to separate out during gel electrophoresis. But before you do that, you've just got to draw the structure of serine at pH 11. So you had to have there that this is the common structure of amino acids, isn't it? You've got that. But for serine, its side chain is that. Okay, that's the side chain for serine. Now, because we're at pH 11 here, that's an alkaline pH, isn't it? pH 11. So if you've got an alkaline pH, acids and alkalis react together. So nothing's going to happen to that end of the molecule. But because you've got an acid here, then you're not going to get the acid at that point. Don't know why that happens. I've no idea what happens. Okay, so that's the carboxylic acid. And what's happened? Under alkaline conditions, that proton is removed, and you're just left with a negative charge there. Now, as much as that's true for serine, it's true for the other amino acids as well, because the other amino acids had just a CH3 as the side chain and had a hydrogen atom as a side chain. So all of these amino acids are going to be negatively charged. Serine will be, glycine will be, and alanine will be. I think I've got that. They're all singly negatively charged, each one of them. And it's true also for the tripeptide that you wrote as well. That'll be singly negatively charged. And so when you put these onto the gel electrophoresis plate, you've got all of these negatively charged ions all moving, because that's where you put the dot to begin with. So they must be moving because they're negatively charged towards a positively charged electrode. or you could say they're being repelled from a negatively charged electrode. They're all negatively charged, singly negative charged, and so they're migrating or they're moving through the gel towards the positively charged electrode. Now, you're just going to be a little bit careful here in setting up this electrophoresis experiment, because you can't just plug it into the mains, because the mains is alternating current, which means it switches positive and negative 50 times a second. So all that would happen is that these little negatively charged ions would be first attracted one way, then attracted the other, attracted one way, then the other 50 times a second, and they would go nowhere. So you've got to not have alternating current, which is what you get from the mains, but you've got to have a power pack here, which is direct current. And so they're just checking your understanding that these negatively charged ions are moving under a consistent, stable electric field, and so F is a direct current power pack. And that allows these negative ions all to move consistently in one direction towards the positively charged electrode. So G is positively charged, H is negatively charged, and I mean, you've just got to know there that in electrophoresis, you usually have a block of gel. Sometimes you might have a filter paper. It's more typical to have a gel. And because you want all these ions to be negatively charged, they've all got to have a pH about 11. And to keep things at a pH 11, then you need a buffer. And that maintains the pH at a particular value. And so the examiner was looking here in this last point that you had to both say you had a gel or a piece of filter paper, and that was saturated or soaked with a buffer solution pH 11. And under those conditions, all the negative ions move to the left as we look at it. And then you had to distinguish between the ion that had moved furthest and the ion that had moved slowest. Okay, so this one's moving fastest, isn't it? This one's moving slowest. And because they've all got a single negative charge, you can't say one is moving faster than the other because there's more charge. They don't. They all have a single negative charge. So the only difference between these components is that they have different relative masses. And your clue was that you had to work out a relative mass earlier on. So don't do a question and forget about it and move on. The question is leading you through, and because you had to work out a relative mass here, that's going to help you, it's your friend, to work out the answer later on. So this S is the tripeptide. That's the tripeptide. Because it's moving slowest, it's got the 3 amino acids joined together, it's the tripeptide. And then you've got to work out, well, which of these then has the smallest relative mass and is going to move fastest? Well, when you look back here, the only difference between these is this side chain. And that side chain is the most massive, that's intermediate, and that side chain, just a single hydrogen atom, is the lightest side chain. So the amino acid with the hydrogen atom as a side chain only is going to be the lightest amino acid, and that will be moving the fastest. So the heaviest one is here, the lightest one is there. Okay, this comes up again and again and again. If you wanted to break up a tripeptide or a protein into its constituent amino acids, then that's called a hydrolysis reaction. Very common question there. And you've got to specify again here, just one mark, both reagents and conditions. The reagents is typically acid. So you've got dilute acid in water, or you could do it with dilute alkali. and the examiner is expecting the condition there to say heat. So the examiner is looking for, you're working hard for 3 marks here. You're looking for acid, water, heat. Or you could do hydroxide ions, water, heat. But you have to get 3 things down there for 1 mark. Seems quite hard to get your mark there, but you must say water, acid or alkali plus heat. Okay, this was Hess's law question. People just go wrong on these because they rush with their calculators. There's nothing difficult about that at all. If we've got time, we'll go over it at the end. That's easy to do. The only reason you're going to go wrong is if you're rushing with your calculator and you punch a number in. Okay, I'm just running out of time here. Basically, with this one here, you've got either chloride ions like that. Can you see that I'm writing my ammonia the right way around as well? I've written it as H3N over here, NH3 over here. Sometimes they knock off marks for that. So you've got that, or you've got the other isomer, which is that, isn't it? And now I'm drawing H3N over here. You've got these 2 isomers, and you've got to explain why they're both colored and why they have different colors. Well, you should know that d orbitals, there's 5 of them, and normally they are degenerate, which means they have the same energy. You fill them in when you're filling up electron configurations as having the same energy. But when you have these complexes here, you have something called crystal field theory. You can look that up. And these ligands split up these degenerate atomic orbitals, these d orbitals, into a set of 2 and a set of 3. So you've got 2 orbitals up here, and you've got 3 orbitals down here. And so you've ended up with a small energy gap between these 2 orbitals. We just call that delta E. There's a small energy gap. And that means if you've got some electrons down here, and a photon of light strikes the metal complex, one of the electrons can get promoted from this lower energy orbital up to a higher energy orbital. And as that photon of light is absorbed to do that promotion, then the remaining light is transmitted. And so the color that you see is transmitted light because a photon of one particular wavelength has been absorbed to promote an electron from a lower d orbital to a higher d orbital. So you're getting the vocabulary you could have here is transmitted. You could talk about absorption of a photon. And these different colors are because whether you've got that isomer or that isomer there, this energy gap is different depending on which isomer you have. And so for that isomer, it might be a large energy gap, and for that isomer, it might be a small energy gap, which means that the electron that's promoted absorbs a photon of a different wavelength. And so a different wavelength of light is absorbed, a different wavelength of light is transmitted, and these 2 isomers appear as different colors. Okay, so let's sort of work hard on these last questions in the last part of this masterclass, because this is where students were having some of the hardest, some of the most difficulties. Okay, so step 1, you've got a benzene ring, and then you're ending up with this this complex, this molecule over here. And so what's happening there is you've got your benzene ring there, and you're getting this chemical here. Okay, And you're using something called a halogen carrier, AlCl3. And what happens there is you get this forming, AlCl4 minus, so that chloride ion has come off, and you've ended up with a positive charge there. You see what I mean? And that means that this can then attack that benzene ring, because that positively charged carbocation there is attracted to the delocalized ring of electrons. And so you end up with a mechanism that does, I'm just drawing the start of that mechanism, where you start to form a bond between this benzene ring and this electrophile over here. And that ends up then with that one there. And you're doing something similar in this next step here, because you're doing that, and you put on here that. And the way you're going to do that is exactly the same again with this halogen carrier. You've got, I'm having to work quite hard on drawing. You've got that. When I have a whiteboard, I'm much better at drawing on a board than I am with this pen. You just have to excuse me. All right. And you've got this. And if you have your halogen carrier again, exactly the same thing happens, is that you get that carbocation there, you make that, and you've got that as the halogen carrier again, all right? So then exactly the same thing happens where you get, that's the start of the mechanism, where you start to get a bond forming, because that is an electrophile, and it's doing, undergoing electrophilic substitution with that ring system there. And so these first two steps, step 1 and step 2, are exactly the same mechanistically, because you used a halogen carrier for step 1 and you used a halogen carrier for step 2. Except you've just had this acyl chloride in step 1, and you have this alkyl chloride in step 2. But it's both the same mechanism with this halogen carrier. All right. So that's how you're going through step 1 to step 2. Go from step, this product over here, down to here. Again, you're using familiar chemistry in an unfamiliar environment, because you're very familiar with using bromine and ultraviolet light in the bromination of alkanes. You look at initiation, propagation, and termination. You can do all of that in your bromination of alkanes. And so you're just using that knowledge in an unfamiliar context, because you're now doing the bromination, not of an alkane, but of that little carbon chain on the side there. So this step 3 is just bromine and the 2 there, and ultraviolet light. And that's exactly what you've learned about when you do your bromination of alkanes with initiation, propagation, and termination. And that gives you the step 3. Okay, for step 4 here, you've now got to do a reaction where you've got potassium cyanide. And what you're doing there is you're taking that, and if we were having to write a mechanism here, you've got a delta negative there, you've got a delta positive there, and that lone pair of electrons there starts that mechanism there, and you carry on there. So this is a cyanide anion acting in nucleophilic substitution. And to get that reaction to happen, you need this potassium cyanide in ethanol. And that's the conditions then for that process, for that substitution reaction to happen. And what you end up with is, just do the drawing again for a moment. You've got all of that, haven't you? And you've just substituted that bromine with this. And when you get that substitution happening there, you've extended the carbon chain. This is a typical reaction to make the chain length longer. And that substitution there is a substitution of bromine with a nitrile. That's called a nitrile there that you've substituted. And to convert a nitrile to a carboxylic acid, you have to heat with water and an dilute acid solution again. So the examiners said that all this learning of reagents was done poorly by the students. But you can see there, it's actually not too hard, because in this step 1 and step 2, we're using a halogen carrier. So we just use the same thing twice. Step 3, we all know if we had a question about alkanes and bromine and initiation and propagation and termination, we'd be able to do it. So we just have to use that knowledge in an unfamiliar context. You've got here extending a chain, carbon chain by 1. You use potassium cyanide in ethanol. And then once you've made your nitrile, you hydrolyze your nitrile and you make your carboxylic acid. So it looks bad, and it's not very nice having to fill in those conditions there. But actually, when you break it down, it's a lot, I think, probably a lot easier than it first appears. You can specify your reactions there. Okay, question number 10, a bit of an odd one here because it just starts off with this sort of strange work with spinach. But really, you've just got to plow through some equations there. We can go over that at the end if you have to. It's just working with concentration, working out amounts. I think that's fairly straightforward to work through all of that. Okay, so this one down here, this reagent down here, you can see they like to do this quite a lot. You should be familiar with that functional group. It's called an acyl chloride. I've noticed they do this a lot. So you learn in your revision or your textbooks all about an acyl chloride. And just to throw you off, what they do is they just put 2 acyl chloride groups together. So there's nothing particularly frightening about that. It's just you keep working with the reactions of acyl chlorides. But in this case, there's 2 of them. And sometimes you get, for example, I think we saw one earlier in the question, that looks a little bit more frightening, but all you've got, of course, is 2 carboxylic acid groups, and they'll just react like any other carboxylic acid group. So don't get thrown by having these 2 lots of acyl chloride groups rather than just working with the single acyl chloride group. And these acyl chloride groups are very reactive because there's electron withdrawing in that direction towards the chlorine. There's electrons being withdrawn in that direction towards the oxygen. And so you end up with not just a slight positive charge there, but quite a large positive charge. And that means that that carbon atom is ready to be easily attacked by nucleophiles. And that's why these acyl chlorides are very, very reactive. And if you react them with an alcohol, then they form an ester. And if you react them with an amine, then they form an amide. And all that's happening, you have to spot here, is that here you've just got one functional group in the molecule, but here you've got 2 functional groups in the same molecule. So that functional group will react there, and that functional group will react there. And so you're just going to end up, if I draw this then, so that's the chemical we started with. And then you've got one amide group there, one amide group there, and you've got a carbon atom there and a carbon atom there. And so this is all easy stuff if you were just having a single acyl chloride reacting with a single amine. But because you've got a diacyl chloride and a diamine, you end up with this cyclic compound here. And all you've done is you've formed two amide links here. All right, good. Well, we're out of time for this masterclass. We can follow up with you guys in a moment if you want. So I think the thing with this one here is you just have to note that particularly with these carbon-13 NMR spectra, is that all it's asking you to watch out for is that when you get a peak, that means you've got a carbon in a particular environment. So the carbon environment here is different to the carbon environment here. And so when you end up with 3 peaks, all that's telling you is you've got carbon atoms in 3 different environments. And that kind of clue is what gets you through the rest of this question. You can see here when it comes to looking at the spectra, that means there's 1 carbon environment. That means there's 3 carbon environments, and that means there's 2 carbon environments. And so that clue about carbon environments is what gets you through the rest of this question here. And we've run out of time here, but that was the question that the examiner said it wasn't just discriminating, and it wasn't very discriminating, but lots of students left it blank. So make sure you check that one in the mark scheme, and then you can work back and just work out the clues that you get by knowing that these have 1, 3, and 2 carbons in particular environments. Well, that was a bit of a monster of a paper. Trying to get through a 2-hour paper in a 1.5-hour masterclass was a bit of a challenge. We didn't quite make it. The Z coaches from Cambridge Leadership College are available, of course, on the Slack channel. And of course, they'll be delighted to follow up with any students who've got questions from this exam paper in the Slack channel over the next week. So all it remains for me to say is to wish you every success with your chemistry studies and look forward to seeing you in the next masterclass.